Okay, so I'm going to go through this video pretty quickly, trying to cover the topic in 5 minutes or less. So you might want to pause the video and take notes when you get a chance. Here's the system we're trying to solve. You're supposed to use reduced row echelon form. But before we do that, I thought, well, let's just solve it using addition elimination to see where we're headed. Okay, so I labeled the equations A, B, and C, and using addition elimination, our idea is to take two pairs of equations and eliminate the same variable. And I noticed that I have negative y plus y plus y, so it's easy to eliminate the y. So if I add a and b, I get 12x minus 4z equals 6. Once I saw that, I said to myself, if I divide by 2 every term, I'll make the numbers smaller. So I did that and labeled that equation D. And then if I add A and C, the y's also will disappear. There's the result. So now I'm going to take D and E and eliminate one of the letters from them. So I can see that if I subtract D from E, the x's will disappear. So I rewrote E and D here. Subtract means multiply by -1 and add if you want to think of it that way. So z is 3. Now plug 3 in for z in any one of these two equations and solve for x. And finally take these two values and plug into one that has x, y, and z in it and solve for y. There's your answers. Okay, so the solution set is 3/2, -4, and 3. Okay, now reduced row echelon form. Here are the operations that you can perform on a matrix that you still have an equivalent system. You can interchange two rows. You can multiply or divide a row by a non-zero constant, or you can take a constant multiple of one row and add it to another row. And so here's the matrix that we create. We put the x coefficients in column 1, the y's in 2, the z's in 3. And we call this an augmented matrix because we put the values or the constant terms in this additional column here. So this is a 3x4 matrix. And Gaussian elimination, Gauss-Jordan elimination, is the same thing as reduced row echelon form. Okay, and our goal is to perform these operations on the starting matrix and make it look like this. If we do that, then we have the value of x here because 1x plus 0y plus 0z equals 1.5. So x equals 1.5, which is what we got. This would be y, and this would be z. Question is, what's the technique for getting from here to here? Well, here's the starting matrix. Our idea is to work first on column 1, and we want to get a 1 here, and then zeros in the remaining rows of the first column. So how can we turn this 4 into a 1? We divide by 4. And here is the notation that we use to mention the operation we're performing. Row 1 divided by 4 goes to row 1. So divide by 4, and then we're going to use that third operation, a multiple of the first row added to each of the other two rows. We're going to take -8 times the first row and add it to the second row. The way they say it is we take row 2 and subtract 8 times row 1. That's another way to think about it. But this is what you end up with. We're done with the first column. And now we want to move on to the second column. We'd like to make this 3 a 1, which we can do by dividing this row by 3. And then we'll add multiples of row 2 to the first row and the second row to make these zeros. And will be at 2/3 of the way there. There's what it looks like. Here's where we were on the previous board. We divide by 3 to make this a 1. Then we add multiples of row 2 to row 1. So we multiply, you can visualize, we're going to multiply this by 0.25 and add it to this row, and that'll become a 0. But we have to do that for every element in that row. So we're multiplying this by 0.25 and adding to negative 0.75. And that's where we get the negative 1/3. Now, it conveniently turns out that after we perform that operation to make this a 0, this becomes a 1. But if it didn't, we'd have to divide, like if this was a 7, we'd have to divide by 7. But there it is. We're almost there. Now we have to work on column 3. And we won't, this is already a 1, so we just have to multiply the third row by negative 5/3 and add it to the second row, then multiply by 1/3 and add it to the first row, and we've got our reduced row echelon form. Okay. If you want to use a calculator, like if you have a Texas Instrument, second matrix is what we're going to be doing for all these operations. If you press second matrix, you get these options: names, math, edit. The first thing you want to do is go to edit, and that allows you to enter the 3x4 matrix. And as you type a number and hit the enter key, the cursor will move to the next operation. You can't see the first column over here to the right. But I've entered the matrix. Then I hit second matrix again. And this time I went to the math column and scrolled down to this row B where it says RREF. I hit the enter key, and I've got RREF displayed here. Then you got to get A. Well, I hit second matrix again and go to the names column and just position on matrix A. And then I click the enter key, and there's your reduced row echelon form for matrix A. And there's your answers again: X, Y, and Z. Okay, now where did I get all those notations on boards 2, 3, 4, 5? I got it from this online Gaussian elimination calculator. You can change the variables. Normally they come up standardly as x sub 1, x sub 2, x sub 3. I change them to x, y, z, enter the coefficients, click solve system, and that's what I get. Okay, there you go. That was a little longer than I had hoped, but hope that gives you the idea.